So guys, welcome back. Today we continue with section 4.3 about the Kronecker product. And this is mainly the outline for today's presentation. I'll talk about the introduction of the Kronecker product, the definition, the formulation, and I will talk briefly about two-dimensional discrete Fourier transforms. Okay, so in section 4.1, in fact, we described the discrete Fourier transform of, in fact, a one-dimensional signal f. And this section 4.2 will describe the two-dimensional discrete Fourier transform, which is needed for images processing. Now, some of you may wonder, why do we have to study this if we are not doing electrical engineering and if we are not working on image processing? Well, guys, you don't know what your career in data science would lead you to, okay? Some of you may land in chemical engineering companies. Some of you may land in multimedia companies. Okay, so you don't know what's going to happen. You don't know the opportunities, about the opportunities that we presented at you. So let's move forward. Let's see the application, in fact, of data science to this field. So when the one-dimensional transform uses a matrix of size n, the two-dimensional transform, in fact, needs a matrix of size n squared. And the 2D matrices here generated will be large. So what we are aiming to do is to construct them easily from Fourier matrices f and omega. This might be okay. So in fact, this construction uses what we call the Kronecker product. And it's usually noted here by f times f. And if you are using the LaTeX, it's O times. The correct symbol for this is /O times, okay? And omega times omega. In fact, the earlier word for this Kronecker product was called the tensor product. And the MATLAB command is Kron, K-R-O-N, of the two matrices you are dealing with, okay? So let's see the definition. In fact, this definition is extremely convenient for many purposes. And this section develops the key ideas and operations on K, the matrix K you could obtain by the product, the Kronecker product A by B, to invert K, and to solve also the system A times B times X equals Y, and to find the eigenvalues at the end and the eigenvector and SVTs of A times B. Okay, so this is the intention of the whole section. Today we'll start but here. Okay, so we'll do just half of the job. And the first thing to know about the Kronecker product is the size of, first of all, A times B, which is usually called Kron AB. So in fact, if A and B are n by n, then A by B is in fact n squared by n squared. Okay, so imagine the huge size of the resulting product matrix. If A is m by n and B is capital M by capital N, then the product AB has m by m rows and n by capital N columns. And in fact, the entries of A by B are all m by n entries of A times all m by n capital entries of B. And the next fact is that the position of those products is about the positions of those products in the large matrix. What is the rule to be used to get this product? Is to multiply each entry of A by the whole matrix B. So this is what we will get, in fact. So if you assume that you are computing the product A by B using the Kronecker product rule, so every block is a multiple of B. So A multiplied by B will give you A11B till A11N. So you see, if originally you got in the first row of A11, A12 till A1N, then you see what is the resulting first row. Okay? So imagine what's going to happen with the next row. Of course, every entry in the second row of A will be also multiplied by B. And in fact, in every entry here you see in the resulting, you have a matrix. That's why this matrix is, in fact, let's say n by n multiplied by m by capital N. Okay? And the simplest case, in fact, has identity matrices for A and B. So in this example, we can easily check it. We have I2, which is the identity of size 2, multiplied by the identity of size 3. And the result is the identity matrix of size 6. How come? Because when you multiply this I2 matrix, where you have ones in the diagonal, by this I3 matrix, what's going to happen? The result is going to be that the first one here, that item is going to multiply the I3. So basically, you're going to place I3 here. And then the 0, which is the next item in the first row of I2, is going to multiply I3. So basically, you get a 0. Okay? Then in the second row, you're going to have 0 multiplying I3. So you get 0. And basically, at the end, you get 1 multiplying I3. So you get I3 here. Okay? So, and as you can see, since this matrix I3 has a whole diagonal of 1s, so basically you will have here in this resulting matrix, you have a whole diagonal of 1 if you assemble them, so you get I6. Okay? And this is maybe the simplest way to see this. Okay? Now, a harder case, any question on this, guys? Well, a harder case comes from multiplying the two Kronecker products. Let's say, usually, if you have A by B multiplied here by C by D. So what is this kind of multiplication? This is the usual, what we call the dot product, usually used for matrices if they share the definition of the dot product for matrices, of course. So the result here is this beautiful property where you have AC, so A by B multiplying by C by D gives you AC multiplied by D. Okay? Moreover, if you multiply the product AB by the product of A inverse by B inverse, you get I by I, the Kronecker product of I by I. In fact, this equation 3 allows rectangular matrices to be obtained, and the equation 4 is for invertible square matrices. Of course, when A and B are invertible matrices square. Okay, so these are the main properties. So if you have I by I, in fact, you get the identity matrix of size small n by capital N, and the previous result in equation 4. So the inverse, in fact, of A by B is, in fact, A inverse by B inverse. And the proof of the equation, the proof of equation of that equation that AC by BD is, in fact, equal to A by B dot C by D could be easily checked. Okay, let's check it on, guys. So this is, first of all, what I'm writing here on this part, on my left part, this is in fact A by B, the Kronecker product A by B. Let's check it on, guys. So imagine you have the first row of A, what is it? It's A11, A12, the second row is A21, A22. So if I perform the Kronecker product, I get the following matrix. Am I right? Okay, so if I multiply it now by CD, okay, so by the product CD, what do I get? I get, this should have been, I think, yeah, this is a dot product, sorry, between, okay. So if I perform now, I do the regular product, so I'll multiply the first row by the first column, okay. So I get A11B by C11D. So this is what I get, A11B by C11BD, as you can see. And on the next item, what's going to happen? I'm going to have A12B by C21D. So I have A12, C21. Okay? So I can put BD at the end as a common factor. And this is what I get. Okay? Now the next component would be by the dot product of what? Of the first row by the second column. Now I'm going to have A11 by C12, A12 by C22. And of course, BD is a common factor at the end. Okay? We can check the third item, which is A21 by C1D. I have here A21 by C11, as you can see. And I have A22 by C21, as you can see. Okay? And BD is a common factor. And the last item, of course, this is a dot product. And the last item would be A21 by C12 plus A22 by C22. Okay? And BD is again a common factor. So as you can see, we've just checked that property. So one can say that when you use the Kronecker product, so A by B dot C by D AC by BD. Okay? And this would allow us to manipulate easily very large matrices. So a matrix of size n squared times a matrix of size n squared is still, in fact, a matrix of size n squared. Okay, if you apply this rule. And the final basic identity produces what we call the transpose of A by B using the Kronecker product. So if you take the transpose of the Kronecker product A by B, is in fact AT multiplied by the Kronecker product of BT. Okay, so you can see that A by B transpose is in fact A11B, A12B, A21B, A22B transpose. So if you just now transpose that matrix, you get A11BT, and here this item would shift to this position. So you get A21BT, A12BT, A22BT. Okay? Got it? So these are some of the main properties we can see with the Kronecker product. Okay. Now, I'll talk about now the introduction to what we call the two-dimensional discrete Fourier transform. So as we can see, as we've seen in 4.1, we've seen the one-dimensional. Now let's suppose that we are starting with the n by n image, and this image could be a photograph. In fact, with n squared small pixels taken by your phone. If you remember, we talked about image and image processing when we talked about PCA and SVDs, if you recall. And we have, in fact, for these n squared small pixels, we have, in fact, n squared numbers. And we have a choice. What is the choice? We could, in fact, unfold those numbers into a long vector of length n squared. And we could keep them in fact, n by n, in an n by n matrix, so that pixels which are close in the image remain close. Okay? So we can use the structure, the idea here, what is the idea? The bright idea is that we can use the structure of the image to use, in fact, the Kronecker product. The Kronecker product would be used to, in fact, let's say to draw the frame or the structure of the image, and the unfolding into a vector by an operator called vec will be described later. In fact, so for now, what we think of is that we think of a vector f in R squared, so it's two-dimensional, with its n squared components in a square, and we intend to apply the 2D, the two-dimensional discrete Fourier transform to f, and the result will be, in fact, a 2D vector C. Instead of what we had in 4.1, we had a one-dimensional vector C from that. So let's see the definition. So that was the introduction to two-dimensional discrete discrete Fourier transforms. So what we could think of is that this process could be split in two steps. First of all, we do a row by row. Okay, so we apply the DFT to each row of pixels separately. So we apply a one-dimensional. This is 1D. Okay, sorry for the, it doesn't appear well here after compiling. So we apply the 1D DFT to each row pixels separately. And then we do column by column. And we then rearrange the output by columns and transform each column. And the obtained matrix for each step is n squared by n squared. So I have an example after this slide. So let's first think of n squared pixels, a row at a time, and multiply each row in that long vector by the one-dimensional DFT matrix. Okay, sorry guys. I think there was a disconnection. So let me continue. So do you hear me guys well?
Yes, yes.
Okay, so I got disconnected for a couple of seconds. So I was saying that first we think of n squared pixels, a row at a time, and multiply each row in that long vector by the one-dimensional DFT matrix, omega n. So if you think of it, in fact, we define what we call the omega index row here, times f. So this is f. What is f here? It's a two-dimensional vector, okay? But it has been separated into rows. So we have row 1, row 2, row 3, row n. And here we have what we call omega row, which is, in fact, the omega matrix placed in the diagonal, okay? And transposed to be able to multiply it by f. So f and omega row f have length which is n squared. Okay? So the properties that follow is that omega row is in fact equal to the identity matrix multiplied by the Kronecker product by omega n. And it's in fact it is the Kronecker product of size n squared. And the output, omega rho by f, is rearranged into columns. The second step we talked about, how the 2D transform, multiplies each column of that halfway image we just obtained by omega n. And again, we'll be multiplying a matrix omega column now by a matrix omega column of size n squared. And the full 2D transform is in fact obtained, which is omega n by omega n using the Kronecker product. And in fact, that matrix we just talked about here, the omega column, is the Kronecker product omega n by the identity matrix n. So the 2D transform puts the row and column steps together into omega n, omega index n by n. So what is omega index n by n? Is omega column by omega row, and in fact it's the dot product omega n of the Kronecker product omega n by omega n, and the identity of size n by the omega n. So you get omega n by omega n. Okay, so let's see a small example before we close this. So if you consider that you have a size n by of 4. So what is n squared? N squared is a kind of 16 pixels in a square. So the block matrix you obtain, which is omega 4 for 2D transform is in fact 16 by 16. And let's write its details. So omega 4 is in fact omega 4 multiplied by the Kronecker product by omega 4. So if you multiply it here, you apply just the basic rule of the Kronecker product, you get the following matrix. So if the omega 4 multiplying the second omega 4, you will have in every first entry here in the row 1 omega 4, and of course also in the first column. And then you start multiplying every entry in the first omega 4 by omega 4 itself. So you get minus I squared, minus I cubed, and as follows. So this is omega 4 by 4. That matrix, in fact, has to be divided by 4 times 4, so by 16, to correctly match the 1D transform, which is omega 4 divided by 4. And the inverse of this 16 by 16 matrix, because this matrix is in fact 16 by 16, gives the two-dimensional inverse discrete Fourier transform, which is F4 by F4 using the Kronecker product. If you apply the inverse formula we've seen before for the property of the inverse using the Kronecker product, which said that A by B inverse is in fact A inverse by the Kronecker product multiplied by B inverse. Okay? If you apply the inverse formula for the Kronecker product, you get the following, that the 1/16 multiplied by that matrix omega 4 is in fact the Fourier matrix size 4 multiplied by the Kronecker product by the Fourier transform of size 4. And you have in fact a Kronecker product of one-dimensional inverses. Okay, so that's it for this first half of section 4.3, guys. So we talked about it hopefully